So let's first discuss what conduction current is. Conduction current is what we took before. It's due to the motion of charges through some surface. And in the next slides coming up, we're going to be showing another kind of current. That's why we want to just mention what conduction current is, and then we'll discuss the other current when the time comes. We want to first outline the problem or the issue that we're trying to talk about. It's basically Ampere's law, the way we took it before in a previous chapter. If you take any closed contour, I call it here a closed loop, but it's a closed contour, any closed contour. Like for instance, imagine a rubber band. That's a closed contour, and you can make it of any shape you want. It doesn't have to be even in the same plane. It could be in any plane. It could be not in one plane. And imagine you have some currents that are going through the surface bounded by this contour. So you have here current I2 going this way, current I1 going this way. Current I3 is not going through the surface that encloses the loop. So this was Ampere's law. We said that the integration of B dot ds, if you integrate the magnetic field dotted into the elements of length ds, these green vectors are the elements of length ds, around the closed contour, the right-hand side, it says it should be mu naught, which is a constant, times the current enclosed. Current enclosed means you only take the current or the currents that are going through the surface that's bounded by this contour. So this was Ampere's law. If you don't remember it exactly, go back to what we did before because it was done in detail. We said also before that we can change the right-hand side. Instead of saying mu naught times I, we know that the current in general can be written as integration of J dot dA, current density dotted into area. But we said before also in detail that we need to make a very specific choice of the relationship between the ds vectors and the dA vectors. If the ds vectors are going around this way, then you use the right-hand rule as drawn in the picture here. You put your fingers in the direction of the ds vectors, then the thumb will point in the dA vector direction. Because for this surface, for instance, there are two different directions for the area. You could make it go up or down because it's an open surface. No, we have to make it very specific. And if ds and dA are not related in this way, then this equation will not be correct. So this is a criteria for making this equation correct. You have to have this relationship between ds and dA. Again, this was discussed in detail before, so if you don't remember, go back and see what we did before. So that's, so far it's fine. This is what we've done before. Comes the issue. If the closed contour, this closed contour, is not in a plane, but it's in general in any shape in 3 dimensions. For instance, you get a elastic band in a closed loop elastic band and reshape it in any direction you want, any shape, so it's not in one plane. Then the question becomes, which surface do we mean when we want to calculate this integral? To calculate this integral, you need to choose a surface. So which surface should we take? It might be, you might think it's easy to find the surface if the contour is in one plane, then you can just take the surface that's in the same plane as the contour. But what if the contour is in 3 dimensions? It's not in the same plane, there's no unique surface to calculate this integration through. What if I, for instance, take this curved surface? This surface can be imagined, if you know, like the game that they have where they have the wire and they put the wire into soap and then they blow the soap bubble and it becomes elongated like this, and if you blow more it can actually make a bubble and go off. This is exactly the same kind of geometry. You have a closed contour and you want to make a surface, any surface that's bounded by this closed contour. So there are an infinite number of surfaces that are bounded by this contour. This one that I try to draw in a kind of 3-dimensional way is one of them. So if you take this surface instead of the other one, the flat one that we took before, and you calculate integration of J dot dA, will you get the same answer? This is very important because if it doesn't give you the same answer and there's no unique surface, then this equation really has a problem. There's a problem here. So if this is basically where what the problem comes from. So if you want to write a law like this, such that the right-hand side will work for any surface bounded by the closed contour, if you want to write the law in this form, we need to see if this integral is the same for all the surfaces. If it's not the same for all the surfaces, then there's going to be a problem, because if you calculate this right-hand side for say the flat surface, and you get a number, and you calculate this surface integral for the curved surface, you get a different number. That means you're getting a different value for the magnetic field. The magnetic field is a unique value. If you integrate B dot ds around this loop, you should get a unique value. So you can't have a right-hand side that depends on the kind of surface you're choosing. So this is where the gist of the problem is, and if you don't understand this part, try to understand it better, and if you have any comments, write down some comments, and I can explain things better. But this is important before we move on. So let's, for instance, give an example. Let's say you have a wire like this with a current in it, and we're not showing the rest of the circuit, and you have here a contour that's in the shape of a circle, and the circle itself, that could be one surface 1, and then the curved surface could be surface 2. And in this case, if you take integration of j dot dA through the flat surface, surface number 1, or through the surface number 2, you get the same answer. It's the same current that's going through both. So there's no problem, there's no confusion. But can you think of a situation where this won't work, where you evaluate integration of j dot dA through one surface, it gives you one value, and through another surface, and it gives you a different value? Well, that exists, for instance, when you're charging a capacitor. If you're charging a capacitor, this is the plus plate, this is the minus plate. Let's take, again, the contour to be the circle, the perimeter of the circle. And then let's calculate integration of j dot dA through the surface number 1 and see what that will be equal to. Well, surface number 1, the current going through it is just I. So the right-hand side will be mu naught times I. If you take now surface number 2, that's going between the two capacitor plates in a region of space where there's no motion of charges. There's no conduction current going in this region. And so integration of j dot dA will be 0 in that case. And so that means that if you write down the equation to be the right-hand side to be integration of j dot dA for any surface, it doesn't work in this particular situation. So in this equation cannot be valid in general. It can't be true always for any situation. So there's a problem. And the solution to the problem, what was proposed, is what if we add a new term called the displacement current? This is the conduction current that we talked about before. Let's add a new term called the displacement current. And let's see what the displacement current looks like. You're integrating E dot dA through the surface, the same surface that you're calculating integration of J dot dA through. So this is a surface integral. It's the electric flux through the open surface, whatever the surface is, as long as it's bounded by the closed contour. So you calculate the electric flux, then you take the derivative with respect to time. So if the electric flux is changing with time, then this term will start to have some value to it. And the idea is if you now have these two terms, then the confusion that happened before will be resolved. Let's see how that will work. So we can say that the conduction current, IC, is this one, and ID, the displacement current, is this one. And we can write down the law this way then. So let's look and see if this resolves things by going back to this example of a charging capacitor. You have a capacitor, of course this is connected to a circuit, I'm just not showing the circuit. And you have charge on this plate, positive charge, you have charge on this plate, negative charge. And assume in this case that there's no fringing. Assume that the electric field is all uniform here and it's going between the two plates and there's no fringing of electric field outside. So let's say you have your contour, which is the perimeter of this circle. And surface number 1 is the flat surface, which is the circle, the surface of the circle. And so we want to integrate B dot ds around the perimeter of the flat surface. So we said you have two terms. You have integration of J dot dA through surface number 1 and integration of E dot dA with the derivative with respect to time of that. Now for surface number 1, this flat surface, there is a conduction current And integration of J dot dA just gives you the current, the conduction current. But surface number 2, surface number 1, there's no electric field here. So there's no change in electric field here. And so this gives you a 0. There's no displacement current through surface number 1. So that means integration of B dot ds is mu naught times I. Okay, what about if you take any other surface that's bounded by the same perimeter of the circle, like this one, that goes inside the capacitor? So it goes in the region between the two plates. So now let's try to calculate the two integrals for that surface, for surface number 2. Now, integration of J dot dA is 0 through surface number 2, because if you look at surface number 2, everywhere on surface number 2, there's absolutely no charges going through that surface. So there's no conduction current at all. So you get 0. But when you look at surface number 2, there is an electric field on the surface, at the region of the surface here. And so it's plausible that if you get the electric flux through this part of the surface and you take a change with time, look at how it changes with time, there could be, this could be non-zero. If the capacitor is charging, so if the electric field is changing with time, because the capacitor is charging, more and more charge is being added here and more negative charge here, then this term will not be 0. And so let's try to calculate what this term is. So let's look at surface number 2, the curved surface. It's equal to integration of E dot dA through this smaller surface. Why? Because over here there's no electric field. We're assuming in this case that the capacitor is kind of an ideal capacitor where the electric field is always constrained to be in the region between the two plates. So if you look over here or here or here or here, there's no electric field. The only place where you have electric field will be this, through this curved part. So if we get integration of E dot dA through this surface number 2, all we need to do is to calculate it through this curved part, the darker one. Let's look at this piece of surface, the darker one. Now, if you look at that surface, the curved part, and let's make a small circle here that makes this into a closed surface consisting of the curved part and the flat part. Of course, if you want to now apply Gauss's law, says that integration of E dot dA through the closed surface that consists of the flat part and the curved part should equal to integration of E dot dA through the flat part plus integration of E dot dA through the curved part should be equal to the charge inside over epsilon naught. But there's no charge inside this closed surface. This is empty space, so this is 0. And remember that the dA vector for the flat part will have to be pointing to the left because it's pointing from inside to outside. The dA vector for the curved part has to be going to the right like this because it has to be going from inside to outside. The result that the integration of E dot dA through the flat part plus the curved part is 0. This is from Gauss's law. And so that means one is the negative of the other. And so if you look at integration of E dot dA for the flat part, it's a negative number. Why? Because the electric field is going to the right and the area vector is going to the left. There's an angle of 180 degrees between them. So integration of E dot dA through the flat part is simply minus electric field times the area. But you have another minus here, so you get minus minus gives you a plus, which has to be the case. The flux through the curved part only is a positive number, and it's equal to E times A. Integration of E dot dA is through the curve. And now we go back to the surface 2, which is what we wanted. We wanted to calculate integration of E dot dA through the surface 2, so it's equal to E times A. Go back to the original equation. We said that the first term for surface number 2 is 0 because there's no conduction current through surface number 2. There are no charges physically moving through surface number 2, but this term is not 0. Now we found this integration to be E times A. That's right, E times A. Now, what's the electric field inside the region of a capacitor? Sigma over epsilon naught. We've done this we'll assume it's like two infinite plates. The electric field between them was sigma over epsilon naught. And what's sigma? Over the area. So you have the area will cancel with the area, and the epsilon naught will cancel with the epsilon naught, and you get dq by dt. You get mu naught dq by dt. But mu naught dq by dt is equal to current. Mu naught times the current. dq by dt is the current. So you get, for surface number 1, the flat surface, you get integration of b dot ds is mu naught I. For surface number 2, you get integration of b dot ds is mu naught I also. So there's no problem now anymore. You get the same value no matter what surface you take. You get the same value. The reason why you got mu naught I here is because of the conduction current. The reason why you got mu naught I here is because of the displacement current. So you get the same value for any surface you choose. If you had fringing, let's assume you have a capacitor that's not kind of, the plates are not close to each other and the plates are not large compared with the distance. So you have some kind of fringing like this, the electric field goes outside somehow. There's no problem. I mean, it's not a problem. Still, if you take the surface number 1, in this case, you will have both a conduction current and a displacement current because you have some electric field going through surface number 1 now. So you'll have some value for both. And for surface number 2, you'll only have a displacement current. There's no conduction current. And when you calculate that displacement current for surface number 2, you'll find that it's equal to the sum of these two. So it should work out anyway. It will always be correct. Whatever surface you take that's bounded by the same closed contour, you'll get the same value for the sum of these two terms.